Okay, today I'm going to start a new topic, the solid element. Okay. For all the previous learning, we learned three different types of the two-dimensional problems. And for those two-dimensional problems, I'm sorry. For those two-dimensional problems, we developed the two-dimensional elements to solve the problems. Today, the solid element, which is the typical three-dimensional problems. And for other structural models, usually we can say there are some kinds of the geometric characters. For example, for the plane stress problems, it is a thin plate. So the thickness of the plate compared to the dimensions on the plate, which is much smaller. And for the plane strain problems, the dimensions along the z direction, we assume it is close to the infinity. Okay, so there is always some kind of the spatial characters for those structural models. If we talk about the solid element, you can say it is a three-dimensional structures. Almost all the structures, all the structures, they must be the three-dimensional thing. And for problems like this one, you can say we do not have any spatial characters, and we need to pay attention and to do some spatial. So the solid structures. All dimensions, they are relatively close to each other, so we cannot say any one of the dimension which is much smaller than others, or for any dimension which is much larger than others. We cannot find anything like this one. So all dimensions need to be considered. Okay, so it means the no very small or very, very large, no such kind of things. It is the typical things for the solid element. So for a structure like this one, we need to consider okay, so for a structure like this one, it means that we need to consider all possible strains and all possible strains. Okay, there is nothing we can neglect or something like this one. So for solid structures, okay, there are three normal strains. If we define a three-dimensional orthogonal coordinate systems, then for these three, it means that we need to consider the normal strain along all the three directions. So we need to consider the normal strain along the x, y, and the z, all three directions. And also we need to consider all the three shear strains, the gamma xy, gamma yz, and the gamma zx. Okay, so that's the for three-dimensional structures, all possible strains. Okay, so we need to consider all of them, and also we need to consider the three normal straits and the three shear straits. Okay, all the three normal straits and the three shear straits, we needed to consider them. And for a structure like this one, no matter if we like to describe the geometry of the structure, or we like to describe the applied loadings, and after we solve the solutions for these problems, and we need to describe the displacements of the considered point, and all of these, we need a set of three-dimensional coordinate system. So it is a 3D problems. Okay, usually the 2D or 3D, usually it represents the coordinate systems we need to use to describe all these things. And for the solid element, it is a typical three-dimensional structural models. Okay, take the prints. Okay, so the coordinate system, we need to the user needs to define a set of 3D coordinate system. Usually we use the x, y, and the z directions. Okay, after the user define the coordinate system, then he needs to define the elements. He needs to define the nodal points used by this problem. And usually we say he needs to mesh the problem. Okay, the mesh means he needs to define the element, how does he cut the structure into several elements. And also he needs to define the required nodal points. The required nodal points, it depends on the type of the element he likes to use. Okay, so that's the procedure. He needs to define the mesh. So okay, let's say it is a typical or sometimes we say that's the real element. Okay, let's take a typical element as an example to check how can we define the geometry of this element, and how can we define the displacement functions used by this element. Okay, if I use the terminology, the real element, probably you can expect then we have a masked element. Okay, so usually the real element is mapped to a masked element, and after we define the xyz functions in the masked element, also we will define or assume the uv and the w function in the master element. After we define all these functions in the master element, then we will do the inverse geometric mapping. We will map the points in the master element back to the real element. Okay. However, in the same time, we not only define the point-to-point inverse geometric mapping, also we will send the assumed displacement functions in the master element back to the real element. Okay, so that's the procedure. And for the solid element, all these procedures, they are similar. However, right now we need one more degree of freedom. There are three coordinate systems. So everything we need to do is not only for two-dimensional problems. Right now we need to define it for the three-dimensional problems. Okay, so I will draw that's the master element. Okay, that's the master element, and usually we use the Greek letters to represent the three coordinates used in the master element. Usually we use the Xi, eta, and the zeta. Okay, it is not so important. The pronunciations or something. Just we use three characters to represent the coordinate system used in the master element. Also, you can see I draw the axis in the center of the element. Okay, so you can expect the Xi values used by the master element. It is the change from the -1 to +1. Also for the eta value, since the origin is at the center of the element, so the eta value it is also changing from -1 to +1. The zeta is also -1 to +1. The reason why we like to use the domain for all three coordinates range from the -1 to +1. Right, okay. Since later we like to use the Gaussian quadrature to do the numerical integration for these problems. Okay, I think that's the most important things we like to use this type of. Okay, so that's the master element, and there are 8 node element. Also, we have the 27 node element. And the next one is the 64 node element. Okay. What is the 8 node element? The 8 node element, it means that we use only the corner nodes. So all the 8 corners of the master element, we like to define the nodal points located at those locations. Okay, so the 8 node element, it means all the 8 corners. And the 27 node element, it means we have 9 nodes on each plane. So for the zeta equal to +1, the plane on the top, you can see 9 nodal points. The 9 nodal points means when we develop the shape functions, we use the quadratic Lagrange interpolation functions. So along all the directions, we use 3 variables to define quadratic functions. Okay, so we have 9 nodes at the top surface. Also, we need 9 nodes at the center. For the zeta equal to 0, you can also see 9 node points. And at the bottom, it is another. We have another 9 nodes. So totally, we need to use 27. And the 64, there are 4 layers, and in each layer we have 16 node points. Okay. Okay, so that's the number of the node points. When you define the mesh for the problems, first things you need to know is how many node points we like to use in the mass element. And we need to define the same number of the node points in the real element, okay? And the definition for the node points used in the real element, the program user who likes to use the program to solve the structural analysis problems, he is the person in charge of defining all the node points required for each element. Okay, so there are 3 types. However, it is not so common to use even more node points. Most of the time, the first one, which is the most common element used. Okay, so we have the real element, we have the masked element, and also we need to define the geometric mapping. The geometric mapping will send the nodal coordinates to the masked element, which is a point-to-point mapping. And we will send the information for the node points in the real element, send it to the corresponding node points in the masked element. So that's the mapping. Send something originally they are defined for the node points in this element. They will be sent to the corresponding node points in the masked element. That's the mapping procedure. Not only the xi, yi, and the zi will be sent to there, and also the assumed nodal displacements ui, vi, and wi. Okay, the xi, yi, and the zi, they are the nodal coordinates. And the ui, vi, and the wi, they are the displacements along the x, y, and the z directions. And the displacements, they are assumed. Right now, we do not specify any values to those values. You can say, right now, the nodal displacements, they are arbitrary real numbers. So it can be any numbers, but we don't know the values of them right now. Okay, so that's the input data nodal coordinates. That's the assumed nodal displacements. And all these informations will be sent to the masked element. Okay, so you can take a picture. Okay, so that's the x, y, and the z functions defined in the masked element. Originally, the xi, yi, zi, they are the data for the discrete points. Only for those nodal points we have the input nodal coordinates. But if we use the shape functions, they are used to interpolate the data from the discrete points to establish continuous functions. So if we multiply the nodal coordinates by the shape functions, then we can establish a continuous x functions. Okay, so after we define these three formula, you can say for any point inside the masked element, not only the points inside, also for all the points on the surface of the masked element, we have the defined the xyz function. Okay, so for these three formula, it means that we define a continuous functions in the masked element, and also for the u, v, and the w functions. Okay, and usually they are the same type of the shape functions. Although in the early studies, some research they try to use different sets of the shape functions. For example, he could use 8 nodal points to define the xyz functions, and he used 27 nodal points to define the u, v, and the w functions. And this type of the formulation, they are called the reduced parametric element. Most of the time, we use the same number of the shape functions for the xyz functions and the same number of the shape functions for the u, v, and w functions. If the number of the nodal points for these two sets of the equations, if the numbers they are same, they are called isoparametric element. Okay, so but I didn't mention that we could use different numbers, since the almost right now, for my understanding, almost no one used the different sets. Almost all the analysis, we use the same number of the shape functions for both xyz and u, v, and w. Okay, so right now all the analysis they are made by using the isoparametric element. So there are another two possibilities. One is called the superparametric. The superparametric means the number of the shape functions, which is great. We use more shape functions for the xyz, and less functions for the u, v, and the w. That's the superparametric. And the other one, should be named as the. Okay, so also we have, but right now, almost all the analysis they are made by using the isoparametric element. Okay, so that's the UV, XYZ function, the UV and the W functions. And for this corner, if all the Cauchy and the eta and the zeta values, they are equal to -1, then the phi for this one, which is equal to L1 of Cauchy, L1 of eta, L1 of zeta. For this point, we need to multiply 3 Lagrange interpolation functions for multiply them together. If we use 8 node element, then the L1 will be make the for the c equal to positive 1, you will get the function value which is equal to 0. And the L1 of negative 1 will give you the value of positive 1. And also, that's the same for the L1 of eta. L1 of eta, if the eta is equal to positive 1, the function value will be the 0. But if the eta is equal to negative 1, the function value will be positive 1. Okay, so if we multiply these 3 together, then you can get the phi function for this point. And you can follow the similar derivation to derive the shape functions for all other nodal points. But if it is 27 nodal points, then for the L1 of c, the L1 of c will make L1 of c equal to 0 equal to 0. L1 of c equal to positive 1 also equal to 0. But the L1 of c equal to negative 1, it will be the number of 1. Okay, it depends on the number of nodal points you used for this element. Okay, then you can derive the corresponding shape functions for all the nodal points. Okay, so take the points. Okay, after we define the shape functions, also you can derive the Jacobi matrix. What is the Jacobi matrix? Okay, you can say the Jacobi matrix, the formula in the previous page. You can say they are the formula define the point to point when we do the inverse geometric mapping. The 3 formula x equal to summation xi times phi, and also the other 2. They can define the point to point inverse geometric mapping. But if we like to know a vector in the mass element, how this vector will be mapped back to the real element, then you can use the formula. Since the d c d eta and the d zeta, and also when I add the d value, when I say it is d c, the d c, it means it is an infinitely small change of the c. So the vector cannot be a very long vector or something. And since it is the derivatives, so it means the d c, d eta, and the d zeta, all of these 3, they are infinitely small values. And if they are infinitely small values, then how this small vector will be transformed back to the real element, then we can use the Jacobi matrix. So the elements in the Jacobi matrix, okay, since the x functions, it is functions of the c, eta, and the zeta, and the x functions which is defined in the previous page. And if we know the x is a function of cosine eta and the zeta. If we like to know the dx, how the x functions will be varied, there are three parameters. If we change any parameter, the x functions also will be changed. So if we like to study the change of the x functions, then we need to multiply the partial x to partial cosine times d cosine plus partial x partial eta times d eta. Okay, we need to multiply all these three by the d cosine, d eta, and the d zeta. Then we can get the dx. And this formula comes from the calculus. And you need to refresh your memory. How can we get the dx from this formula? Okay, so that's the formula. If we have this one and the first row of the Jacobi matrix multiplied by the d cosine, d eta, and the d zeta can give you the dx. It is the mathematics. And okay, so the other sixth term. Okay, there's for this. And also remember, the Jacobi matrix can be calculated. Since we know all the xy, xi, yi, and the zi, also we know all the shape functions. So since we know the shape function, we know all the phi functions. So we can calculate the partial derivatives of all these functions. So we can calculate the partial. So how do we calculate the Okay, so remember the xi, they cannot be changed. All the nodal coordinates, they are input from the user. You cannot change the input nodal coordinates in the from the beginning of the analysis until the end. The xi, they are always the fixed value. And so when you take the chain rule, this one no need to be changed. It is a constant. Only the phi function, they are functions of the cosine eta and the zeta. So when we take the partial derivative of the x to the cosine, it will be the summation of the xi times partial cosine partial phi, and we can calculate these functions. And the partial derivative of the phi to the cosine, it is also it is still functions of the cosine eta and the zeta. So for any given point in the mass element, the given point means we know the values of the cosine eta and the zeta. So if we know the location of this point, then we can calculate this term. And also we can calculate all the elements in the Jacobi matrix. Okay, so for any given point, the Jacobi matrix can be calculated in real numbers. Okay, for any point we can calculate the Jacobi matrix, the 3x3 matrix in real numbers, and also we can calculate the inverse matrix from the elements in the Jacobi matrix. Since we know all the elements, we know their values, so we can calculate the corresponding inverse matrix. So the inverse matrix can be Okay. First, we need to calculate all the elements in the Jacobi matrix. We need to calculate them in real numbers. Then we can calculate the J inverse matrix, and also all the elements in the J inverse, we know their values. Okay, and the elements, they are calculated from the J matrix. Okay, and then you can say okay, since this vector is equal to J times d c d eta d zeta, if we multiply the J inverse to both sides, then we have the J inverse times dx dy dz. J inverse times J, it is a unit matrix, and the unit matrix can be neglected, since the unit matrix times d c d eta and d zeta, it is still the same, the same vector. So you can say J inverse multiplied by this vector is equal to this vector. Then you just follow the mathematics or the theorem learned from the calculus. Then you can write the meaning of the elements in the J inverse. What is the corresponding value of this one? So that's for this one. And what is the okay, since the term d c is equal to the first row of the J inverse times the dx, dy, and the dz. So the first row of the J inverse should be these three. Okay, can print the screen. Okay, I think I will take a break here and continue it the next hour.